My name is Skylar McCaw, and welcome to my Lab 2 video about the motion of a falling object. In this lab, I recorded a video of a styrofoam ball falling and used Tracker to analyze it and get data. I then used some of this data, such as the initial velocity and position, to create computer models of the experiment using GlowScript. The first model attributed the entire net force to the weight force, and the second model included both the weight force and the drag force. I then compared the graphs both these models produced to the one from Tracker to see which one was a better model of the actual video. The goal of this experiment was to look at how different forces affect the velocity and position of an object, and how said forces work separately as well as in unison. Many of the equations from Lab 1 carry over to Lab 2, with a few additions. First of all, we must continue to use the velocity and position update equations when creating the computer models of the motion. The ball's velocity is used to find Fnet, and then the updated velocity uses said Fnet and is used to find the updated position for the graph. There are two new equations that must be used as well though, the weight force equation and the drag force equation. The weight force equation is equal to negative mass times gravity times I hat, and the drag force equation is equal to b times the velocity squared. Here's the video I took loaded into Tracker being analyzed. The ball started to fall at frame 55 and ended at frame 77, for a total of 0.734 seconds of airtime. I did not have to add any tilt to the coordinate system at all because the ball fell perfectly straight. The ball itself was 0.035 kilograms and had a diameter of 0.0533 meters. The data collected from this Tracker model indicated that the initial position was 0.0007723, negative 0.001540 meters, and the initial velocity was 0 meters per second, and the initial time was 0 seconds. The frame rate was also shown to be 29.97. I then used this information in the GlowScript code to alter it to fit my experiment. I changed the initial velocity and position to the vectors I had found, made sure that the gravity was set to 9.8 meters per second squared, added in the mass of the ball, and changed delta t to match my frame rate. For this first program, I was only using gravity for the force, so b stayed at 0. I changed the while statement to go up to 0.734, the length of my experiment, and had to alter a few of the other equations to get proper results. This included adding a new line for the weight force and setting it equal to the equation from before, the mass of the ball times gravity squared, I hat, and setting Fnet equal to the weight force. I also had to alter the position update formula and the velocity update formula to match the equations from Newton's second law. This is now the final code for the gravity-only model. I took the data from Tracker and put it into a spreadsheet, then took the data I obtained from the GlowScript code and made a graph comparing them. The two lines are very far apart, and the code drastically overestimates the distance that the ball fell. This means that there were potentially various other effects and forces coming into play that affected the descent of the ball. One such force is the drag force. This force slows the ball down through interactions between the ball and the fluid air. Taking this into account in the computer model would therefore produce a graph more similar to the experiment than the one does not account for the drag force. So let's make a new model. Much of the previous code we created stays the same. The info found from Tracker remains, and the equations for updating position and velocity do as well. The main thing we need to adjust for is Fnet, and this is done through the creation of a new variable, f sub d. F sub d is the drag force, and is set equal to the equation b times the velocity squared. In this case, b times the magnitude of ball that fell squared times I hat. And Fnet is changed to w plus f sub d. In doing this, we are creating another new variable b, which is currently set to 0. The next task is to find an appropriate value for b. This is done through testing and checking. One must test a variety of different b values and see which one makes it so that the final position of the computer model is the same as from the Tracker data. For my experiment, this value turned out to be 0.0906. Using the new computer model, this is the graph I created, comparing the other model and the experiment itself. While it is much closer to the experiment line than the first model, it is still not a great model of the experiment. Many issues could have arisen during the experiment and the evaluation to have caused this discrepancy. One that I think occurred was that the ball had a spin on it when I released it, and that caused it to fall non-uniformly. I also think that the texture and many holes in the styrofoam had an effect on the rate at which it descended. In which of the models is terminal velocity achievable? Well, terminal velocity is when the force of gravity and the drag force equal out and the net force drops to 0. In Model 1, there's no drag force, so terminal velocity is not achievable. For the second model, there is both the weight force and the drag force, so terminal velocity is achievable. Looking at the graph, specifically the yellow line, the slope starts to become more constant within the red box. A steady slope means velocity is constant and Fnet is unchanging, in this case 0. This means that terminal velocity was achieved in the second model. Can terminal velocity be affected by initial force, such as an object being thrown down instead of dropped? The answer here is no. Terminal velocity is determined by the drag force and the weight force, and neither of those have been affected. The thing that is affected is the time at which terminal velocity is reached. Having the object start off at a higher velocity means that terminal velocity will be reached faster than just by dropping it. That is the end of my lab report. Thank you.